Yeah. All right. So your quiz tomorrow will be very similar to this. Notice it says show your conversions. All right. The first one, we're converting from decimal degrees to DMS, which of course stands for degrees, minutes, seconds. Right. And the minutes and seconds are used to convert fractions of full degrees. Like we have here 126 full degrees and 0.351 of a full degree. And then on number two, we're doing it in reverse. We have degrees, minutes, seconds. We want to convert it to decimal degrees. Both of them are measures of rotation, and they're both degree measures of rotations. So here's what you'd have to show me then on the quiz. Number one, we're starting with 126.351 degrees, and we want to convert it to degrees, minutes, seconds. So we already know that our final answer is going to be 126 full degrees. If you want to kind of get your final answer going over there. What we need to concern ourselves with is how to convert the fraction of a full degree. Now, we're going to use stoichiometry by multiplying by fractions equivalent to 1, conversion factors. So if you want to put that over 1, we need to get rid of degrees and convert that to the next unit down, which would be, of course, minutes. There are 60 minutes in 1 degree, just like there are 60 minutes in an hour. So degrees kind of act like hours in terms of time. And then stoichiometrically, that works because notice your degree bubbles, or your degree bubble divides out, and we're left with what units? Minutes. So essentially, what you're doing is you're taking the fractional part and multiplying it by 60. So it's easy enough to think about it that way, but I do want you to show on the quiz tomorrow the stoichiometry. That way I know that you know why it works as well. And you get 21.06. So that's 21 full minutes and 6/100ths of a minute, which is a fraction of a minute. So now we're going to do it again. Now we're going to take the fraction, 0.06 minutes, and we're going to convert it to the next unit down, which is seconds. So minutes in the denominator, seconds in the top, 60 seconds in 1 minute. And stoichiometrically, again, you'll see that your minutes divide out. And you're left with what final units? Seconds, which is what we want. So hard to go wrong when you know that your units are working out. 0.06 now times 60. Really, you could just hit times and it'll recall the answer. Times 60 again. Oops. Is that what we want? No. See, I did a careless mistake there. I took the whole answer. I just want the 0.06 and then multiply that by 60. 3.6. 3.6. Now that's 3.6 seconds. So I'm going to write that down. Now, if there were a unit that we were using that was smaller than seconds, like microseconds, nanoseconds, we can convert the 0.6 down to something smaller, but we're not going to. So at this point, if you have any decimals left on your seconds, you're going to just round or truncate to 3 decimals. This one terminates at 1 decimal, so we're essentially done. So your final answer off to the side here is 126 full degrees, 21 full minutes, and 3.6 seconds. And the division between the degrees, minutes, and seconds, there's no commas, there's no awkward space. The units themselves become kind of the division. So that's exactly what you would write right there. And we're done. That's it. Now, you can check on the calculator, as I mentioned in class on Friday. And after the quiz, after you do this on the quiz, then this is how you can convert in the future for the rest of your life. Tomorrow is the only time I'm going to make you show me the how, the why, the behind the scenes. If you type in 126.351 and you go to your angle menu, which is second apps, 3 clicks above the number 7, notice number 4 is convert to DMS. So if you select number 4, it shows up. You hit enter, and boom, you can now compare that to the answer you got. And you're like, dang, the calculator is as smart as I. Well done, calculator. I will keep you as a tool. And if you get a different answer, then you can, I don't know, trust your ability to type in versus trust your ability to convert. You got fix the answer. All right, the second one, converting from DMS back down to decimal degrees. Now we're starting with a negative angle. Oh boy, can we have negative angles in this class when we're talking about angle measures? Yeah, apparently so. This is kind of a segue into today's lesson and a review of what we did on Friday. Angles in this class are vectors because we're not doing Euclidean geometry, we're doing coordinate geometry. So we're always going to have an initial ray that is on the positive x-axis. Whereas in Euclidean geometry, you never really made the distinction between which one was the initial and which one was the terminal, as we're going to call it. You just had two rays, and the arc was drawn between the two rays, and that defined the angle. And of course, if you didn't draw the arc, and this probably wasn't an issue in geometry, but someone might mistake that as the angle you're looking for, right? And so that's why it's important to draw the arc. It fixes the two rays so they don't move outward, but it also defines the angle. And theta, remember, is not just the name of the angle, it also represents the angle measure. But in Euclidean geometry, if I ask you to draw an angle, you could draw it any one of these. You could draw it small or big, and it doesn't change the angle measure. It changes the length, but not the angle measure, and you can rotate it anywhere you want. So that's why we have in coordinate geometry a standardized version of that so that we all look at the exact same angle in the exact same way. So if we were to put that on the Cartesian plane so that the vertex is at the origin and the initial ray is on the positive x-axis, a negative angle then is going to be a rotation from there. Which direction? Clockwise or counterclockwise? Well, remember, a counterclockwise rotation would be rotating upward, and that's the positive. That's the positive rotation, which is why the quadrants are labeled like that. That's quadrant 1, that's 2, 3 is down here, and 4 is down here. They're labeled as you rotate them in the positive direction. So a negative angle is actually going to be in the clockwise position. Okay? And so a negative 274 is going to actually rotate, of course, in the clockwise direction. So let's see where that would live. This would be negative 90. This would be negative 180. And 3/4 of the way around would be negative 270. So it's kind of helpful to know where it's partitioned. This would be negative 90 degrees. This would be negative 180 degrees. This would be negative 270 degrees. And of course, going nowhere would be 0 degrees, and coming full circle would be 360. So negative 274 would just be a little bit past the y-axis, and it would be right there. So let's give this guy a name. Let's call him theta. And now I can label it as theta there. So that's where my angle lives. And you don't have to draw that on the quiz tomorrow. Or maybe I will, because we're going to talk about that today. But for this particular conversion, it's not necessary. So here's what I need you to show me tomorrow. We have two units here, minutes and seconds, that are both already existing that need to be converted to degrees. So you're going to do this one in one step instead of sequential steps. They're also negative, yes. Now the negative makes it a little bit more dangerous. We got negative 274 degrees. That one's good. If you just say plus 25, now you've made a serious mistake, because the first one's negative and the second one's positive. When you add them together, they're going to cancel. So we want them both to be negative, as you just mentioned, Trevor. So minus 25 minutes over 1, and then we're going to multiply by a conversion factor. I want minutes to divide out and degrees to appear. So 1 degree is 60 minutes. So essentially we're dividing by 60 instead of multiplying by 60. And then minus 11 seconds over 1. We want seconds to divide out. And instead of going through minutes like we did at the end of class on Friday, it's easier if you just know how many seconds are in an hour. How many seconds are in an hour? 60 seconds in a minute, 60 minutes in an hour, so 60 squared, or 3,600. So same thing with degrees. There are 3,600 seconds in 1 hour. And that's worth remembering, unless you just want to divide by 60 twice. 3,600 seconds in a full degree. And notice stoichiometrically, in the first term, or the second term actually, your minutes divide out, and in the second term, your seconds divide out. So now all of your terms have the same units of degrees. And they're all minus because we started with a negative angle. Now, if you don't want to make them all negative, here's another way you can do it. You can actually put like a beefy bracket out front and then add them up inside the bracket and then just make your answer negative at the end, however you want. But you better not have anything canceling out. I'm just going to keep them all as negative. Now, once you have that set up, now you can go straight to your calculator and type it in exactly as you see it. So here we go. Negative 274 minus 25 divided by 60. And then minus 11 divided by 3,600. And the reason you want to do it in one step is because those two pieces from minutes and seconds are probably going to be decimals. And you don't want to have to write down any intermediate decimals. You just let the calculator store them all at one time and you write down your answer. And there it is. It's negative 274.419 degrees. Or, if you're a rounder, be careful, it's 420 degrees, and now you need that third decimal because it's part of the accuracy. They're both correct. If you ended up with an angle that wasn't negative 274, then that means your signs are wrong, because there are for sure 274 full degrees, and that should be in your final decimal degree answer as well. Now, is there a way to do that one on the calculator? Well, I showed you all on the angle menu, again, second apps. There's convert to DMS. You have rectangular to PR, P theta, P. I don't know what those are. But there's nothing in there that shows you how to convert from DMS to decimal degrees. But notice, number 1 has a degrubble on it, right? And number 2 has a minute symbol on it, a tick mark. So there is a way, and I'll show you that way right now, which tomorrow on the quiz, feel free to check. If you type in your original angle now, 274, negative 274, let me try that again, degrees, go to your angle menu, second, apps, and type number 1. It actually puts a degrubble on it. Sweet. And we wanted 25 minutes, so then just type in right after there, 25, go to your angle menu again, select number 2, minutes. Sweet. And 11 seconds, that's going to be 11. Go to your angle menu and just type in seconds, which is a double tick mark, which is which number? 2 again, right? 2 twice, right? Because minutes mean seconds. Unfortunately, it doesn't work that way. But that's good thinking. That's good thinking. There has to be a reason why they didn't put the double tick mark there. It would have been nice if they would have just had 9 menu choices and made number 3 the double tick mark, right? So you might infer that since they don't have it, you're just going to use the single tick mark twice. It doesn't work. So, dang it, TI, why didn't you give me the double tick mark? I guess because they want you to do it the old-fashioned way, dividing by 3,600. Well, not really. A double tick mark also resembles a quotation mark, doesn't it? And a quotation mark is used when you're talking like, boy, I love math, said Jim, right? You would put quotations around, boy, I love math. Your calculator has alphanumeric characters. So maybe there's a quotation marks under the alpha keys somewhere. The alphas are your green keys. Do you see a quotation mark anywhere on your alpha menu? The plus sign has a quotation mark. So let's try that. Let's hit alpha plus. Hey, and it showed up as a double tick mark. Now let's hit enter. Oh, yeah. All day long. Thank you, TI. You actually made the double tick mark easier to access. You put it there on the face of my calculator. I don't have to go digging through any menus. Sweet. So tomorrow on the quiz, you could check that using that method, but I'm going to make you show. It doesn't work that way. That's the way you want to do it right there. Okay. Any questions on converting? All right, let's jump back to the notes then. We don't need to do examples 1 and 2 because we just kind of did that in the warm-up. So let's go ahead and define now what we just talked about, an angle in standard position. We are talking about coordinate geometry, not Euclidean geometry. So again, we want to standardize all of our angles. An angle in standard position has its initial ray on the positive x-axis, as we already mentioned, and the terminal ray, which is the one we end at, so we are now naming the rays. It may land at anywhere in the 4 quadrants, including on the x or y axis themselves. A counterclockwise direction is a positive angle, and a negative angle is a clockwise direction. All right, so do we need to define that again? Very quickly, let's do so. We're going to need some x and y axes here, so I'm going to draw one set. You can use the snap feature, which is kind of nice. There we go. Okay, so the vertex is at the origin. Here's your initial ray. Initial means what? Initial means infinity? The initial, like of your name, is like the first letter of your name. So initial means starting or first. And I'm going to draw it over here. What the heck? This would be what we call the terminal ray. And terminal means what? End, right? So we have a starting ray and an ending ray. We call them initial and terminal. And the angle is the measure between them. And we usually label that with a letter, like theta. This would be, of course, the positive or negative direction. Positive. So we want to draw the arc there, because without the arc, it's confusing whether we want that or the other one. So I'm going to call that theta. And in this case, just for what it's worth, again, counterclockwise represents a positive angle. But I can also get to that same terminal ray by starting at the initial ray and rotating the clockwise direction. Let's call that one alpha. A clockwise direction is going to be a negative angle. Now, someone looked this up. Who was it? Was it Bridget? Did you look it up? If I look at the magnitude of theta, which is a positive number, so that's not going to change it, and then I add to it the magnitude of alpha, that should equal how many degrees? 360 degrees, because it makes one full rotation. Two angles that add up to 360, I kind of threw in at the end of class, as Bridget threw it out to me, are called what? Explementary angles. That's a good trivia question. They add up to 360. You really didn't have a need for that in Euclidean geometry, but here it's kind of nice. Because within one rotation, positive or negative, there are actually two angles that will land at the same terminal ray. They're not the same angle, but they land at the same terminal ray. And those two angles' magnitudes always add up to 360, so their magnitudes would be explementary angles. There you go. All right, so in example 2, what we want to do is just come up with maybe a plausible, I didn't even call this example 2, come up with a plausible degree measure for the following, bless you, angles. Now, if you notice, the terminal ray is the only one that needs to be shown, bless you. There is no initial ray shown. Why is it okay not to show the initial ray? Yeah, we'll assume everybody knows where the positive x-axis is, and the x-axis is already drawn. So you don't need to draw it again. You don't even need to draw the arrow on the arc, because the direction is implied, because you're always starting on the positive x-axis. If you want to draw the arrow, that's fine. It is a vector. So because that one looks like it bisects the first quadrant, let's call it theta. What is a plausible measure for theta? 45 degrees. I like it. 45 degrees. It cuts the 90-degree quadrant in half, so it's 45 degrees. All right. Let's assume that all of these angles, these terminal rays, bisect the quadrant that they're in. What would then be a plausible measure for this angle, which I'll call beta? Negative 225 degrees. Good. Because it looks like we're going 180 degrees in the negative direction plus another 45. So 180 plus 45 equals 225. Now that's bench work, so I don't have to put my degree bubbles on there, and I don't have to worry about the sign. That's the magnitude of the rotation. The fact that it's negative is because it rotates in the clockwise direction. Good. So remember that beta in this case represents not only the name of the angle, but also its measure. Holy moly, look at the next one. That one's crazy. It's like going around like a whole time, and then it's like, okay, this is where I really wanted to go. So that would be a full rotation, which would be 360, plus another 45, so it looks like it's going to be about 405. Let's call this one alpha, and we'll just say it's 405 degrees. If you don't put the degree bubble on your final answer, would you lose a point? Say yes. Yes, good, okay. Not good to lose a point, but good that you know that you lose a point, so you can avoid losing a point. All right, oh, talking about crazy. This one's crazy, all caps, crazy. It's going around a full rotation plus another half rotation plus another 45. So that's like a 360 plus 180, another half rotation plus another 45, which ends up being 585? Is that right? Okay, let's call this one that. What's that letter? It's another typical one that I use. That one's phi. So we had that conversation on Friday. We typically use theta as the most popular. Alpha, beta go hand in hand pretty nicely. Phi. But really, right now, any Greek letter would suffice. And that's positive because we're rotating counterclockwise. I don't know. We're going to get away from Greek letters and start going back to just plain old X and Y. I don't know. Why not Hebrew letters? Greek letters are easier to draw, I guess. I don't know. And because we're talking about angles, I don't know. It's an important enough shift that we shift alphabets. It's not like we ran out of, regular, what do we call our alphabet? English alphabet? All right, example 3. Now we're going to draw them. So here's where if you want to come up here, or maybe redraw one set, we're going to need a set of X and Y axes. And I'll use gray in this case. And I'm just going to copy and paste it. All right, so 190 is theta. Clockwise or counterclockwise? Counterclockwise, so you don't have to draw the initial ray. Just draw your arc. We're going 10 degrees past 180. So ultimately, I'm really concerned with you being in the correct quadrant. But if you can, try to draw it representatively in the correct portion of the quadrant. In this case, we're only 10 degrees past 180, which is just a smidgen past. So draw it closer to the x-axis than to the y-axis. If you label that theta, you're good to go. Sweet. Letter B, negative 276. So let me just paste my little x and y axes in there. This one is going to be clockwise or counterclockwise? Clockwise. Now 276, let's see, there's negative 90, negative 180, negative 270. Again, it's helpful to know where your angles are. And we're only 6 degrees past that, so it's just a smidgen past there. And we will draw the terminal ray, which should have an arrow on it. And then we'll label that as beta. And you're good. All right, letter C. Phi is negative 91. Negative 91. Can you look at that and tell me what quadrant that's going to live in without drawing it? Quadrant 3. Good. Negative 90 takes you to the negative y-axis, and we're going just a single degree past there, a 360th of a rotation past that y-axis. Phi. D, alpha is 629. Oh boy. Now we're getting kind of a large angle there, 629. That's more than one rotation, right? But 2 full rotations, as you know from skateboarders, that's a 720. That's a big trick. Yeah, so how do you know it's in the same place as the last one? You've already done the math. You could take 629 and subtract 360 from it, right? And you get 269, which is going to take you 1 degree short of the negative y-axis, which if you look at the previous example, we were also 1 degree short, but we got there by going 1 degree past in the clockwise direction. But notice that they do land the same spot in the coordinate plane, don't they? They're both 1 degree off of the negative y-axis. They just get there in a different fashion. So they share a terminal ray. Would you agree? Are they the same angle? No, those are two very different skateboard tricks. A negative 91, not a very big trick. A 629, a better trick. But they both share a terminal ray. All right, E. Oof. Oh, it does. Sure. Yeah. We could do that. If you want to show that, that's fine. I'm not going to be real picky about showing that because you're going to get angles that go around like hundreds and hundreds of times. So you're not going to actually have to show that. But maybe for a small like this, you could draw a little spiral. Thank you for pointing that out. I didn't address that. I'm not real interested in that. I'm more interested in where does it land within one positive rotation. Can you get it in the right quadrant? But yeah, for what it's worth, we can go around once and draw a spiral. We'll continue that here on part E, I guess. But not when we get to F. All right, 1822. Now, instead of subtracting out 360 by hand, you will have your calculator for this. So here's what you could do instead. 1822, let's subtract 360 from it. And you get 1462. That's another angle that is a full rotation away that lands at the same spot, right? 1462 and 1822 are different angles, but because they land at the same spot, they share a terminal ray. But that's not going to necessarily help us. So let's just take that and subtract 360 again. So if you just hit minus 360, it'll recall the answer. 1102 is another angle that shares a terminal ray, but really doesn't help us in sketching it. Now here's the cool thing about the calculator. Once you do something twice in a row, your calculator remembers what you're trying to do. So now if you just hit enter after you do it twice, watch this. It'll automatically do it again. 742 is a little bit better. Hit enter again. 382. Oh, that's super close. One more time. 22 degrees. So what do all those angles have in common? 22, 382, 742, 1102, 1462, 1822. They all have the same terminal ray, don't they? They all land at the exact same spot in the coordinate plane. Now, how many rotations did we have there? It looked like we subtracted it out 5 times. So if you want, let's go around 5 times. 1822. 1, 2, 3, 4, 5. Whoa! And you can't see what I'm doing, but you can hear that I'm having fun. Right? It's kind of like the MASH game. Tell me when to stop, stop, stop. And then you count, and then, oh, I'm going to live in a shack. But at least I get to do math. That's my version of MASH. M stands for math. You're going to be a mathematician. You're going to live in a shack. Okay, let's get back to business. I went around 5 full times. Now where do I go? Now I go to, what was it, 22? Good. So now I go to 22, which is about right there. And we'll call that theta. Pretty easy. Now, is there another way to get down to 22 besides subtracting 360 that many times? Okay, hang on. Take 1822 and divide by what? Why divide by 360 and not say, I don't know, 241? Yeah, this is stoichiometry, and you don't actually have to show me that, but you're basically taking 1822 degrees, and you're multiplying it by 1 rotation over 360 degrees. And your degrees are dividing out, and that'll give you the number of rotations. So if it's a large enough angle, simply divide it by 360, hit enter, and that tells you how many rotations you have. We went 5 full rotations, which gives us back to the starting place, which we're not really interested in. It's the 0.06111111 that we want to know. So if you just hit minus 5 here, don't type it in by hand, let the calculator store the decimals for you, hit enter. It's 0.06111 now rotations that we need to convert back to degrees. So to convert from rotation to degrees, we just multiply by 360 degrees over 1. Or in other words, just re-multiply by the same number you just divided by. And you get 22. It's a lot faster that way. Divide by 360, get rid of the full rotations, re-multiply by 360, and you'll get your angle that falls between 0 and 360, which will help you sketch it. All right? Now that might be helpful on the next one. Oh boy, what's that letter? That's omega, capital omega. And the angle is negative 57,631. Now, you could do it this way. You could type it in, negative 57631. But now instead of subtracting 360, because it's a negative angle, we have to add 360. There's once. There's twice. The calculator knows what I'm trying to do. So now all I have to do is keep hitting enter, enter. And notice that all of these angles have what in common besides they're black and they're in the negative 50,000. Oh, no, they're not all in the negative 50,000, but they're still all black. What else do they have in common? They're all negative. But that's soon not going to be the case either. What else do they have in common? They all share what? They all share a terminal ray. They all land at the exact same spot in the coordinate plane. Look at that. Look at me go. These are all different angles, but they all land at the exact same spot. I'm trying to get to the angle that lands between 0 and 360 so I know where to sketch it. And I'm getting closer. I am a persistent fella. That's one thing for sure. Now, thank goodness I have the calculator to help me do all the heavy lifting here because, I mean, not that I wouldn't go home and do all this by hand because that's fun too, but anyway, hey, there it is, 329. The angle, negative 57,631, shares the terminal ray with 329 degrees. That I can work with. What was it again? One more time. I have a bad short-term memory. 329. Okay. Now, in which quadrant is 329 going to live? Quadrant 4. So I'm going to draw a terminal ray in quadrant 4. But I don't want to draw it like that, do I? Because that gets to it by going in the positive direction, and that's not what omega is. So if you want to show all of those rotations, whatever. Okay, just go for a dizzying spin and then have your terminal ray land there. Oh, you could probably do it, right? Yeah, you could probably do it. I'm not going to be that interested in that. If you want to just kind of draw like a crazy spiral to show that it did go around more than once, that's fine. But there it is. There's omega, and we've labeled it. Now, of course, that's not going to be the best way to write omega. I don't like that one. There we go. What's the better method? Negative 5,7,631. And divide it by what? 360. That was negative 160 rotations. Now, instead of subtracting the negative 160, I want to get back. So I'm going to add 160. You want to get rid of the integer part. So whatever the sign is, add the opposite. I'm interested in the fraction of the rotation. So now that I've got it down to the 0.068111, notice more ones showed up, which is why you let the calculator store it. Now you remultiply by 360. But then there's one more thing to do. Negative 31, you probably could figure out where negative 31 is, right? That's just going straight down 31 degrees. What I'm going to be interested in the future is what is the angle that shares the terminal ray with it that's between 0 and 360. I always want the positive angle. So if you wanted to get the next angle that was a full rotation away from negative 31, simply do what? One more time, just add one more full rotation to there, and boom, you get 329, which is what we got. But in all honesty, negative 31, in this case, if you're just trying to sketch it, you could figure out that it gets you there by going straight down. So let me call that one negative 31 degrees. And then the other one, let's go straight around over there, and we'll call that one beta. And it was, what, 329? So there are three angles right now that are different angles, right? But they all have what in common? They share a terminal ray, right? Don't share a terminal Richard. They share a terminal ray. We better come up with a name for such angles that share a terminal ray so that we don't have to keep talking about them as being angles that share a terminal ray. We better come up with a name for them. There were some other there are some other angles that shared a terminal ray. Letters C and D, right? They shared a terminal ray. So what name do we give for two angles that share a terminal ray? I said it. It's coterminal. And this is actually something that makes a lot of sense, to name two angles that share a terminal ray as coterminal, because terminal means ending ray. What does co mean? Share. We cooperate. We share operate. We're two surgeons, and we go in and we cooperate. He does the cutting open, and I do the sewing up. We cooperate. We share the surgery. Cohabitate. We share our habitation together. Sharing is caring. All right, so two angles that share a terminal ray are called what angles? Coterminal. And for any angle theta, how many coterminal angles are there? Infinitely many. And they're all full rotations away in either the positive or negative direction. So in general, we're going to call the coterminal angles theta subscript COT. That means coterminal, and it shows that it's related to theta. All you have to do to get coterminal angles then are start with your original angle theta and add multiples of 360 to it. So what type of number is n? It's going to be an element of z, where z is the what? The integers. Okay? So if n is 1, you're one positive rotation away. When n is 2, you're two positive rotations away. When n is negative 1, you're subtracting 360. So you're one rotation away in the clockwise direction. When n is 2, you're 2 rotations away in the clockwise direction. Can n be 0? Is 0 an integer? Yes, 0 is an integer. So by this definition, when n is 0, you get theta coterminal equals theta. Can an angle then be coterminal with itself? By this definition. Heck yeah. An angle can share its own terminal ray with itself, right? That's the best way to share, right? I'm going to buy a pizza, and I'm going to share it with myself. I'm going to cut it in half. I'll eat this half, and myself will eat the other half. I'm going to share it with myself because I'm hungry. Sharing is caring. I love myself. Yes, an angle can be coterminal with itself. Last example, don't put your calculators away. Example 4. If we start with 465, we want to find all the angles then that are coterminal with it between negative 1,000 and 1,000. So here's the easiest way to do it. I'm going to go ahead and write 465 down. All you have to do is take your calculator, take 465, write it down because it's coterminal with itself. If I add 360, I'm going in the counterclockwise direction. 825, that's less than 1,000. I'm going to write it down. Notice if I add 360 again, though, it's bigger than 1,000. So that's my upper bound. So what I'm going to do now is go back to 465, or maybe just go minus 360, and then minus 360. Remember, if you do it twice, your calculator will remember what you're doing. So hit it again, you get 105, write it down. It's greater than 1,000, negative 1,000. Negative 255, write it down. It's greater than negative 1,000. Hit enter again. Negative 615, write it down. It's greater than negative 1,000. One more time. Negative 975, that's greater than negative 1,000. If you hit it again, you're less than negative 1,000. So once you write all those down, and I wrote them in increasing order, here's your answer. The coterminal angles to 465, all of them, between negative 1,000 and 1,000, are these 1, 2, 3, 4, 5, 6 angles. And notice the angle itself is in the list, right? Right. Okay, we'll stop right there for the day. You're going to quiz tomorrow up through anything we've covered today, including this. Make sure you return your calculator. Get on those corrections. Wednesday is the free response.